rest, l'envelope, and then you can see the fall season and you can see the rainfall. And of course, because it's a three, I mean, there are three stations, so you need three graphs to show that. So, and then we want to see, oh, can we spot differences between these graphs? So, but let me first remind you what is the definition of the Kullback-Leibler divergence, and also why we would like to use it. Maybe some of you have already known about this divergence because it's used in machine learning. If you look, if you're interested in forecasting and scoring rules, it's called the logarithmic score. Of course, in information theory, it's really a good tool to compare two distributions. If you like causality theory, you can also work with that. And especially for people who work in climatology, or they are used to dynamical system or statistical physics, and this idea of divergence is also used there. And in the domain of climate science, if you're interested in questions like detection attribution, that's also a tool. So that also, in some sense, my first constraint would have to have a common tool used by many, many different communities. But mathematically, you could see it in a very simple way. If you take a random variable, let's say x, and then you say the density of the PDF of this random variable is f. So if you apply f to x, then there's a likelihood, but if you take the expectation with respect to x, that's the expectation of log of f of x. And then if, let's say, x is your target, then you want to compare to a different PDF g, then you can do exactly the same computation, but then you just replace f by g. Of course, when you look at this divergence, it's not symmetric, but it's very easy to make it symmetric. You can just switch, oh, this would be x, y, and this would be y, x. When you have to switch it, but that's a typo here, sorry about that. And there is classical properties from this Kullback-Leibler divergence, but basically it's really linked to the likelihood, the expectation of the likelihood. Now we can look at a very simple example. I think the simplest one I could find was a Bernoulli random variable. So a Bernoulli random variable, I suppose everyone knows what it is. You just, try to see like P, which is a probability of winning or losing. You can think about the Nuggets, for example, or maybe the Lakers. It depends on which side you are about that. But in this case, P is probability of X equals to 1, and Q is a probability of Y equals to 1, and you want to compare P and Q. And if you compare the Kullback-Leibler divergence for that, it's just P minus Q multiplied by log of P over Q, 1 minus Q, 1 over 1 minus P. So this is very simple expression. And the plot here is when you have P and Q, and then you have this value here. And so that's a very, very simple example of a divergence. And then you can have something more complicated, the multinomial, for example, random variables. And then you don't have, you have, again, P minus Q, but now you have J, and it's J to say you have different choices. You don't have only 0 and 1, but you can have different choices here. Keep in mind this formula. I will come back later on. So now we have to deal with, if I want to compute this, this is fairly simple. If you are ready to impose a parametric density for f and g, if I say f is Gaussian and g is Gaussian, for example, then I can compute that. So that's fairly simple. But in my case, as I said at the beginning, I don't want to impose a parametric family on f, or neither f or g. So then we need to do something else. And then what I'm going to do, I'm going to leverage extreme value theory for this setup. So at the beginning, I said I'm interested in the multivariate case, but first I will speak about the univariate case because it's simpler to explain. So here, in terms of notation, try to keep this one in mind because I'm going to use it all the time. when I speak about F bar, it means the survival function. Okay, it means the probability of large S greater than small x. Okay, so it's a probability to be above little x. Just as an example, an illustration, if you think it decrease in the term of a power law, x power minus alpha, like the Cauchy distribution, the T distribution, or Pareto distribution, then you could say, well, I would like to compute this kind of Kullback divergence for this distribution here. And L is just a multiplicative function, which is going slower than x power minus alpha. So let's see how we can bring extreme value theory here. So extreme value theory comes because here we are not going to use x, simply the distribution of x or y, but we are going to look at given I'm above a large threshold u. So remember, if I was speaking about rainfall, I said I'm just going to look at very high rainfall. So imagine u is large. So I'm saying, given that I'm looking at very large rainfall, heavy rainfall, then I want to know what is the distribution of x rescaled by u. And I can do that by the second sample y I want to compare with. And then I get the density fu and gu. And then in this case, now it's exactly the same equation than before, except now we have little u's everywhere. So it's nothing new here, it's just a new notation highlighting the fact that u now has to be large if I want to do extremes. And so if I go back to my example here before, for these two types of distribution, if I compare them, then the Kullback-Leibler divergence goes when u gets large to this quantity, which is nice because it characterizes basically the tail index of my two underlying distributions. So that's fine, but still this is parametric, but just an example here. So now I'm going to look at one of the main points of this univariate case is like, I think you have two different types of school, I think, in statistics. You have modern statistics, when with Fisher, people think, oh, we need to look with the log likelihood, we need to look with the densities. And then there's people like Pareto who are interested by PDF, but they are mostly interested by the CDF or 1 minus CDF, the survival function. And why? Because usually when you do extreme, you are more interested not by f of x, but the probability of x is greater than something given that something is already large. So we like to look at a survival function. So, and with Armel Guillou and Theo Rich in 2014, we gave a new expression of the Kullback-Leibler divergence I just defined before, this way. So it looks a little bit more complicated, but in fact it's simpler. So I'm going to try to explain very briefly what I mean by that. What you have to keep from this formula is the fact that before we used to have g of x, okay? But now we don't have g of x, we have g bar. So in some sense, we have replaced the density, the PDF, by the survival function, okay? And then if you do that, you have to pay a price, and it's a delta of u here. But what's happened when u gets large, then this delta is become small. So the story I want to say with this formula here is the fact that if I want to compute for u large, the divergence between the exceedances above the threshold u, then I don't have to know what to try to work with the PDF, but I just need to know how to work with the survival function g bar and f bar. So, and you can see the approximation if I set the threshold u here and I take classical extreme value distribution, you can see the cost for that, the little delta, is very small. But this is just sometimes an example, but in practice, of course, I don't know what is G bar because I don't want to impose a model on G bar, and I don't know what is F bar because I don't want to impose a parametric form on G bar. So if I don't want to impose a specific form on G bar, the best way in some sense to estimate G bar is just to take the empirical distribution, which means G bar now as little n is just the empirical survival function. So if you look at this way now, it's a very simple estimator. And what's nice with that, if I could have gone non-parametric with a PDF, but then I would have to use a kernel or something like that. Here, I don't have to even to do that. I just plug in the empirical distribution, survival empirical distribution for G bar and F bar, and then I have an estimator. Then, of course, there is a classical question you can ask as statisticians love to ask, but I'm not going to spend too much time on that. But you can derive convergence results, which are under the null hypothesis or under the alternative and so on and so forth. So my point is, in the univariate case, it's possible to compute the divergence above large values by just using this very quick formula, and then you have a good estimator of what you are looking for. So I don't know if people want to ask questions now. I'm going just to have a little drink, but if you don't have questions, I could go to the multivariate case, but now there is a question about the multivariate distribution, because it's fairly difficult to have a full multivariate extreme value theory. And so what people do usually in terms of, because before it was easy to condition on X, you just say X is greater than U. But when you have X1, X2, X3, for example, you're in three variate case, it's more difficult to say, should I be above X1 or X2 or both of them or the three of them or whatever. So what people do usually is a condition on a projection of X, which is called R of X. So let me give you a picture for that. What people ask when they do extreme value theory is they like to have an homogeneity condition, which is if you take X and you multiply by a scalar T, then it's going to be just the product of T by R of X. So what could be R of X? So for example, if you look on the left, here I have the threshold U, here X1, X2 on the X-axis, and then this is going to be the max. Here, if I take X1 plus X2 greater than U, and you look above that, is going to be the blue point, or you can take R of X, the mean of X1, X2, and then it's a blue box here. So you can define your extreme by using either this R, the mean, like it's really at the upper corner, or you can use this one, which is a max. And in this case, to have an extreme means that at least one of them is extreme, but maybe not the other one. So, so now we are going to add one more thing in our strategy here, is to say, well, if now I've chosen an R, like X1 plus X2 greater than U, then I'm going to divide the space into different regions, okay? So here I said, oh, I'm going to divide this space where I define what is large into three different regions according to, let's say, a triangle, or it's not really a triangle, but you can see what it is. Of course, I can do this technique to define the space, but here I define it in just rectangles, and I have three rectangles. Okay, so, and now if I go back to my application, remember I have three weather stations in Brittany. This is for the spring and the fall, for example. And then if I look, I can define in 3D, for example, a subspace where we have the red point, the black point, and the green point, which are kind of cones for the extremes. And then I could say, well, what's happening in these cones are the difference between the spring, let's say, and the fall. Okay, so I can divide my space, and then I need to make a few assumptions, and the main one is this one. So what does it say here? It says that given that R of X is greater than U, for example, given we are looking at this region here, and so if I look at the point here, for example, in the orange point, the probability of this number of points divided by all of them is called Pj, and Pj has to be between 0 and 1. It cannot be 0, basically. That's a constraint. And because I have two samples to compare, I have the X and the Y, it's the same constraint for Y. So let me give you an example. It's a bit a special case for that. For example, if you just look in the 2D case, if you take R of X equals max of X1 and 0, and X1 has the same univariate distribution, then, for example, you could have this region here, which should be the R of X greater than U, and then you can cut this region into two parts, either this part here or this part under it. Okay, and this, for example, is called the classical extremal dependence coefficient in extreme value theory. And this means simply that, for example, given like it's raining a lot in Boulder, what's the probability it's raining a lot in Fort Collins? So with this framework, you can get classical conditional probability using extreme value theory. Okay, so now under this framework, you can ask ourselves, well, I would like to test this P equals to Q for any subset, okay? And one of my first slides at the beginning was about the two multinomial distribution. So if you remember, if I have two multi-random variables, I could try to compare that with the Kullback-Leibler, and that's an explicit formula for that. So that's what we are going to use in practice, because if I go back here, I can, in some sense, I'm going to count the number of points here, the number of points here, and the number of points here for sample 1, and the same to sample 2, and then I'm going to compute the Kullback-Leibler for that, which is basically what I'm doing here. Of course, when you do statistics, you like to have a little hats everywhere, so I put the hats everywhere. And then what are the estimator here? Well, because I'm just counting, I'm going to count the number of points in the large set and the number of points in every small subset. And then this is going to give me the proportion I have. So it's very simple statistic and very fast to do. So the main result in some sense now is the following one. If you choose correctly the threshold, so what you want in some sense, what does it say here? In some sense, it said that if I take the number of points in my set of extremes, I want to have a lot of points in that when my sample size grows. Okay, so I want mn going to infinity. So, but respect to n has to go to 0. So every time I increase the threshold, I want to have more and more points in my sample, so my sample size has to increase, but then not as fast as the large sample size. And then there's some technical condition. I don't have time to speak about that too much, but what we can show, it's like under H0, so if P equals to Q, basically, then this divergence go to a chi-square with degree k minus 1. So that's look fairly simple, I would say. But it's kind of surprising because it doesn't depend on how I have chosen A. Okay, so in some sense, I just K just a number of set A, but I don't have to say if A has to have any specific form in some sense for any types of S satisfying my condition at the beginning, then I will converge to the chi-square distribution. And if the null hypothesis is not true, then we can derive these other results. So that's good. But of course, we have a few issues I'm going to talk about now. So we remember we say, oh, we need to choose a threshold UN such that this goes to infinity. Okay, so that's a theory. And then if this is satisfied, that means everything is good. But in practice, to choose UN and Vn that satisfies this, I need to know the distribution of R of X. So R of X is just the projection for, as I said, for example, R of X could be X1 plus X2, or max of X1, X2, or mean of X1 of X2. But in practice, I don't know what is the distribution of X1 plus X2 because I don't impose a parametric form on that. So to solve this issue, we are not going to look at the value of R of X or R of X or R of Y, but we are going to look at the ranks, okay? So because in some sense, if I order my data, then this mean is kind of a quantile. And so if I work with the ranks, now I have an estimator of my P's, okay? So I have fixed this problem of not knowing R of X and R of Y by using the ranks. But there is a price to pay for that. It means that the theory is going to be much more complicated after that. Is it a big deal in practice? If you know the margins, if you know the margin you have, it's always simpler. So here, if you look at this graph, on the x-axis, I have the number of sets. For example, if most of my graph I have the number of sets equals to 3, for example. And here I have the type 1 error and the type 2 error and the power of the test in the red. So it's just for an example here. I'm not going to describe the details of that, but the main point is the power of the test is about 0.7, almost 0.8 here. If the margin are unknowns, then it's a little lower. So you pay a price when you don't know, you lose some information when you don't know the margins. But still, even in this case, you can get interesting results. So I'm going to spend a little bit of time to explain this graph because it's kind of complicated. Here, if you look on the left side, okay, we have Kn, which is a number, or Mn, should be the number of exceedances, okay? So it means that the threshold is getting higher and higher and higher, okay? As I said before, we know that under the null hypothesis, the statistic of the entropy, the Kullback-Leibler divergence, should be a chi-square distribution with degree k minus 1. So this is the black line at the 95 confidence level, okay? So if you look at this graph, it means from this example here, simulated, I know that F1 equals to F2, that means the two distributions are equal, and delta 1 equals delta 2, it means that the extreme distribution dependence function is also the same. So what you can see here is the fact that the blue is under the black line, so it means we don't reject the null hypothesis because by construction, we know that this bivariate vector, which is a Clayton copula, but it doesn't really matter, it means that our tests look good. And here we have repeated the experiment many times. So that's what we get. Now, if I look at a different example, I compare the Clayton copula with the logistic copula. It's two different multivariate distributions, but they have a nice feature in the sense that the two distributions are different for the bulk of the distribution, but they are the same for extremes. Okay, so in some sense, this example, simulated example, show that when the number of exceedances, we look at moderate extremes, then it looks like we are above the chi-square test. It makes sense because they are different for small values. But when k gets large, then it becomes H0 is not rejected anymore, because we know by construction, this example, the extreme rule dependence in the upper tail was the same. So it looks like it's working in this case too. And if I take a case where we have two different multivariate distribution, which are different in the bulk of the distribution, but also in the tail, then you can see now we are above the black line. Okay, so basically, it looks like from the simulation, we did a few simulations, it looks nicely for the simulation. So far, I've only mentioned basically 2D examples in terms of simulation, but now I'm going back to my data. Okay, so in my data, I don't have something in 2D, but I have something in 3D. Okay, and again, we have the same result, so we can apply that. And let's go back to Brittany. So that's in the west part of France. And if I compare the fall and winter in Brittany, so when I say I compare the extreme rule behavior between two seasons. So my question is, does the fall heavy, the rainfall in the fall are different than the extreme rainfall in winter in terms of the dependent structure. And here you can see when I change the number of exceedances, when I look at the more, these become more and more and more extreme when I go from the left to the right, then it looks like, at least in this case, it looks like there's a difference. That's the same graph here, but now I did it for any combination of seasons. So you can see that now we can spot that for some seasons, like if I compare spring and winter, it looks like it's fairly similar, but for other seasons, it's different. So now we have a tool that we can propose to climatologists and to say, without fitting any distribution, you can know if the dependent structure between the seasons are different or not for extremes. That was in Brittany, but if you look at the eastern part of France, it looks like the seasonal effect is very negligible for extremes. That was the eastern part of France. But if you look in the south of France, then the story is different. And this could be explained by different factors. For example, in the south of France, that I think most of you know, it's during the summer, it's also much warmer. And I suppose it's a bit like border. At the end of the day, in the afternoon during the summer, you have very strong convective storm, which are that could bring heavy precipitation. And this could be different from the winter. So in terms of extremes, like in the south of France, the extremes are usually very intense, but very short-lived, but different in the summer and the winter, for example. So this made also climatological sense, I would say, for this example. So I'm going to also give you another example where here, I don't know if you can read it here, but now I'm moving a little bit away from precipitation. Still the x-axis here is precipitation, but the y-axis is not precipitation anymore. This is wind speed. So now we are in the case where the fact we don't know the marginals has a bigger impact because it's very easy to see that wind speed has a very different distribution than precipitation. Okay, I mean the unit is different and so on and so forth. So, and if you look at the original scale, we can always turn that to the exponential scale or the Pareto scale. But here I can still divide my space into 3 different regions in this case and see how this region can differ. But in this case where we look at very different margins with different tail index, then it's possible to prove that for d equals to 2 in 2D with r of x equals the mean, and that's a little bit more technical, but in some sense you have to have some notion about how is the dependence among extreme there, then you get the same, again, the same type of result we have shown before, okay? So that was pleasing. In the case where we have so-called asymptotic dependence, then that's a situation where we don't have this nice result in some sense. As I said before, again, this result is interesting because it doesn't depend on how I've chosen the blue shape, the red shape, or the orange shape. In this very specific case, we don't have that. The limiting result won't be a chi-square distribution, but something more complicated that depends on the set we have defined. But still for this case, when r of x equals mean of x1, x2, and we are in the case of asymptotic independence, then we can do for the application of rainfall and wind speed, then we can do the same type of graphs. We can have the chi-square line here, and we can see if it is above or not, and get some result about that. So I'm almost done. I think it's good. I hope I was not too fast, but I will give more time for questions. So what I'm trying to give you in some sense is to show you maybe that the Kullback-Leibler divergence, which is used in many, many different fields, can be tailored for extremes in some sense. And if you do that, then you don't have even to impose a parametric form to your marginals or your dependent structure. So in some sense, this is nice, I think, because it's easy to compute, it's fast to compute, and you don't have to fit a parametric model. And under various setup, the limiting distribution of this, the estimation of the Kullback-Leibler, the estimator of the Kullback-Leibler divergence goes simply to a simple chi-square distribution, so which is very also easy to handle. In terms of climatology, it looks like we have shown that in the western part of France and the eastern part of France, it looks like the structure, the seasonal structure is not super important, but I didn't write it here, but in the south of France, it's much, much different. What we did in some sense, we would like to have maybe an automatic way to choose r of x, because in most of my example I showed you before, I choose r of x like the mean of x1 or x2 or the x1 plus x2 plus x3 or whatever. So, but maybe there is an optimal way to choose r of x. The number of set too, I mean, we didn't spend time to find what is the optimal number of set. And there is a little more complicated. I mentioned that very briefly before, but when we have asymptotic dependence, then it's a little bit more difficult to handle. But that's, I think, fairly rare in terms of application, I mean, depending. And I think I have a little bibliography here, but I think I'm just going to stop here and take question, if you have any question.
Thank you. I had a question. You might have already said it, but what kind of restrictions do you need on the R functions? Do you need?
Oh, well, there is in terms of the R function. Let's see. Can you see the screen again? No. Well, let me try to,
no.
Give me 1 second. The only constraint basically for the R function it has to be homogeneous of order 1. That means R of, if I take R of x1, x2, let's say, and if I take R of tx1, tx2, that should be T R of x1, x2.
Okay.
So
it's funny. I was just having a conversation with someone this morning about defining the extremes in multivariate cases. So
yes,
this is very timely for me.
Let me go back to this. Now you can see my screen, I suppose.
Yes.
So that's the only, I mean, the rest in substance, you can take whatever you want, basically. Most people take the max, the sum, or the mean, but you could take something even a weighted sum or weighted max. So the choice of R, it's fairly free. What is more difficult to get in substance, you still want to have this. Okay, so what that means by that, it means that like here, when I took this R of X, which is the max, in this example with the 3 different colors, you can see that knowing I have maybe like 50 points here, in each of the subset, I will have points. So I will never get 0. But in some cases, maybe I have one example here or not. Let's see. Maybe here. Well, this is you. I mean, if you. I mean, maybe let me go back here. It's possible sometimes if you are, for example, highly correlated, for example, there will be almost no point here. It could happen. So then in this case, you need to take, for example, if I have no points here or no points here, then it will be better to take this set. Because if this set is like that, then if I cut it in 3 different parts, then I will have points. I mean, the ratio will be always positive and never goes to 0. So,
okay.
And that's on, it's a little bit like when I spoke also about asymptotic dependence or asymptotic independence, which is like nuances in extremes, but this is kind of important at this stage. So that's really where the choice of R of X should be very delicate if you have almost no points in these regions. But if you find something where you can, the ratio, if you take a set and then there is point in it and you can divide it and there will be still point in any different set, then the shape of the shape themselves are not important.
Got it, thanks. Any other questions? Yeah, Francois.
Thank you for a very nice talk, Philippe, and congratulations to stay awake. I have 2 questions. The first one is about your choice of divergence. I mean, you're in Paris, you should be using optimal transport. So why not use, one of your favorite Wasserstein distance or sort of transport distance?
Well, that's a good point. in terms of, we use the Kullback Leibler divergence because it was easy to work with in the first place, and it's still very much used. I think as the Wasserstein distance could be another, and it's a true distance in this case, so in some sense it would be better. But I think we don't know yet how to integrate the multivariate case, because it's not that easy to write down as a Kullback Leibler. In some sense, like here, in some sense, if you look back at this formula here, here it's very easy to do plugin.
Yeah.
And I'm not sure for the Wasserstein it would be that simple. But I think it would be better to do with the Wasserstein. I mean, I don't say better, but I would be a good alternative.
So I have a second question. So under the null, your test statistics is chi-square with k minus 1 degrees of freedom, and so it sort of evoke some kind of Gaussian, k-dimensional Gaussian vector with independent coordinates. But the k is with regard to the region. Those regions are not, I mean, clearly not independent. So what is going on? Am I misunderstanding something?
No, I mean, there are, in some sense, that's the surprising fact. In some sense, it's if you look at this convergence here in distribution,
right?
In some sense, when you count the fact that the dependence between the set A, I mean, when you fix this, let's say I fix the set A1, A2, and A3, when this is fixed and then you count that, it's kind of a counterintuitive, but it's a bit like Poisson almost kind of a aspect. It's like the fact they don't intersect, A1, A2, and A3 don't intersect, they kind of become independent.
Oh, okay.
And in some sense, you could imagine also the size of them. A1, A2, and 3. When I do the plot, they have exactly the same size, but one could be 10 times larger than the other two. That won't make a difference.
Okay.
Which is very surprising in some sense.
This is very surprising. Thank you very much.
And that's, I think, the strength of this result in some sense.
Okay, well, thank you so much for staying up past midnight. It's 1 a.m. for you, I guess, now, and giving us this talk. I think my current students have a lot of new symbols that they just learned that they can recognize. So, everyone, if you would unmute, please, and help me thank Philippe. Then we'll call it a weekend. Thank you.
Yeah, thanks. And well, I hope next time I will be able to come to Boulder in physically. I think there is a I mean, what is it? A conference on geostatistics in Boulder this summer. I think maybe
next summer. Yep.
So maybe I will try to come then. Okay, thanks again. I think I'm going to go to bed.
Thank you again.
Thanks. Bye-bye.
Bye.